Greetings everybody, welcome to the latest edition of the Physics Corner. This is a series of videos in which we show how to set up and solve simple physics problems for introductory physics classes in college. I am your host, Dr. Christopher Sorolla. This is the second of a two-part series on what are called parallel plates. In electricity, we're going to place charges on opposite sides of two parallel conducting plates. So we have positive charges, a plus capital Q here, and an equal amount of negative charges, negative Q, over here. We're also going to have those plates separated by a distance d. Notice that we're measuring from surface to surface. Also, the cross-sectional area of each plate, which is identical, is 0.0025 square meters. Some other facts that we'll need. The total amount of charges on each plate is 5 times 10 to the minus 9th coulombs, or if you prefer, 5 nanocoulombs. The permittivity of free space is this number here. We are using vacuum, so the dielectric constant is 1. And in a previous video, we determined that the electric field strength between the plates is this value, 2.3 times 10 to the 5th volts per meter, and the potential difference between the plates is 2300 volts. Notice I have rounded off the numbers to 2 digits, but of course we can be a little more cautious in our calculations when we do that. What are our questions? Well, today we'd like to address an idea called capacitance. Now, the short version of capacitance is the capacity, or ability, if you will, to store electricity. Now, how do we store that, or how do we describe that? You can describe that as capacitance itself, or if you actually have charges, you can talk about the amount of electric field you've stored. You can talk about the potential difference between the opposite sides, or even the total amount of electrical potential energy that's stored in this system. So there's a variety of different ways to describe it. So if I say capacity, the capacitance is the ability to store electricity, that's a little vague, but that's what we're talking about. Capacitance itself is a specific term though, and it turns out capacitance only depends upon the geometry of the situation and possibly the materials involved. What do I mean? So in a case like this, and this is set up sort of artificially, we have two conducting plates. One has positive charges and the other is negative charges. Now, how do those charges get there? Well, we're not drawing them otherwise, but you can imagine they're hooked up to wires, perhaps, that are themselves connected to something like a battery or a power supply of some sort. We've thrown a switch, we've closed a circuit, and the electrical potential energy from that power supply has moved the charges to opposite sides of the plates like this. So that's a little bit of an unknown that's going, or that's behind the scenes, if you will. That's one way to do it. We're also depicting nothing between the plates because that's the situation. We're assuming there's vacuum between the plates. In actual practice, there'll probably be a material between the plates, say plastic or glass or paper of some kind would fill this gap. But today we're making it simple. We're going to assume that there's actually nothing between the plates and leave it there. Okay. And when I say that capacitance, the ability to store electricity, depends only on geometry materials, what do I mean? So, capacitance for parallel plates specifically is this formula. It is the dielectric constant, which is a material-dependent idea, this permittivity of free space, which tells you the ability of free space to permit electric fields to go through it. Because the value of E naught is very tiny, that implies it's very easy for electric fields to go through vacuum. It depends upon the area, the cross-sectional area of the plates, and it depends on the distance between the surfaces of the plates, like this. Notice it goes as the area, and that makes sense. The larger the area, the more charges you can store, right? So that makes sense. But also notice it depends on the distance between the plates. Think about it this way. The further apart the plates are, the weaker the electric field both sides will sense from each other. Therefore, the more difficult it will be to store electricity, right? So that's kind of a way to think about it. Okay. In any case, by the way, and this is worth mentioning just to say it, this particular formula is for parallel plates only. You can't have a variety of different shapes for capacitors. For this ability, the geometry of the different shapes you have will determine the equivalence of, say, area here and distance here. They'll look different. There'll be different formulas for those. Chances are, in a course like this, if you're taking an algebra-based introductory course, you're very likely to only talk about the parallel plate situation. So we're going to limit it to that in this video series. But there are other shapes that are possible. It's worth mentioning it could be done. All right, let's go ahead and plug in some numbers then. So it's vacuum, and by definition, the dielectric constant of vacuum is 1. Epsilon naught is 8.854 times 10 to the minus 12. And these are the units. A little complicated, but there they are. The area was 0.0025 square meters, like that. And then we are dividing by 0.010 meters here. Okay. So when we do this calculation, we come up with a pretty tiny number. 2.2 times 10 to the minus 12. And the units are called farads. Now, what's a farad? Let's take a look here briefly. We have meters squared and divided by meters squared there. So these 2 meters squared would cancel, but we're left with coulomb squared per Newton meter, okay? Which is kind of a weird sort of conglomeration, and for a variety of reasons, and this is not the only way to do this, by the way, it makes sense to assign capacitance its own unit. That unit is called a farad, okay? It's nicknamed after Michael Faraday, who is an important physicist and chemist and otherwise brilliant experimenter who lived in the middle of the 1800s. Anyway, this is the value of the capacitance. Now, because capacitance values are usually very, very tiny, it's sometimes common to depict the number as with a prefix. And 10 to the minus 12 is called pico, and the prefix is a little letter p. So if you see this, that's what that's talking about, okay? But I will leave it this way because we do want to use that number in our next set of calculations. But that is common to see that. So very, very tiny. Now that doesn't mean you aren't storing anything. One of the things you will remember if you watched the previous video is that even though the amount of charge that's present is very tiny as well, the voltage and the electric field strengths are pretty high. So it's not a given that you can have small amounts of capacitance with these large values. Now, by the way, notice something else though. This is important. This, again, only depends upon material and the geometry. There's no electric field in this calculation. There's no voltage here. There's no potential energy here. There's nothing like that. This is simply the ability of the system to handle or to support or to store electricity. And that does not depend on whether you got electricity there at all in the first place or not. It's like saying, okay, you've got a 5-gallon bucket. That doesn't mean you filled up the bucket with 5 gallons of water. It just means the bucket is able to hold 5 gallons, whether it's full or not. So that's why it's kind of the situation it is. That's why it's the calculation it is. All right, now it's time, though, to put in the actual electricity, okay? Or to say, let's put in the fact that we do have charges stored now. Therefore, we do have electric fields, we do have potential difference, and thus we have electric potential energy, right? So there's a variety of ways to calculate this, but here's probably the simplest one. Now I'm going to go ahead with this usage. This is common for the textbooks we use at my place, but if you see it as a capital U instead, that's also pretty common for as a symbol for potential energy in physics. But in this case, the textbook we're using, potential energy, so it's real obvious. And the E subscript reminds us that it's an electrical potential energy. Also, you might recall from previous physics, you had things like gravitational potential energy and spring potential and so on. Well, now we're introducing a new kind of potential energy called electrical. So this formula, or the formula I'm going to use here, is this one. 1/2 multiplied by capacitance by the potential difference, or voltage, squared, like that. This is a common format for a lot of these kinds of calculations for energies. Not every energy calculation is a 1/2 something times something else squared, but it's pretty common. And so this is a hint, by the way, if you're in a test or some other situation, you're trying to remember a formula for potential energy of whatever kind, chances are it's 1/2 multiplied by some constant feature multiplied by some variable squared. The reason I can call this a constant feature is that, again, this depends on the geometry, right? And supposedly this device doesn't change its shape in the middle of your deliberations, right? But the voltage, which depends upon the charges that you've stored, that's something you have control over, so that's a variable. Okay. All right, enough of that. Let's go ahead and calculate this value too. So we have 1/2, We have our 2.2 picofarads, or 2.2 multiplied by 10 to the minus 12th farads, like that. The voltage, as determined in the previous video, again rounded off, 2300 volts, and that quantity is squared, like that. And therefore, the total amount of energy, I'll write it down here actually, is 5.6 times 10 to the minus 6th joules. Notice that it is units of joules because it is a unit of energy. Okay, just because it's a different kind of energy doesn't change the standard unit. Joules are still the standard units of energy, even though we're not talking electricity instead of, say, kinetic energy or gravity potential. Still energy, therefore still joules. Also, again, since we're seeing a lot of very tiny numbers, 10 to the minus 6th is micro, and so a way to do that with prefixes, I would say 5.6 microjoules is another way to write that answer. So it's a possible way that you might see it this way, but more likely than not, you're going to see this. All right, everybody, and that is a short version of how to calculate the capacitance of a set of parallel plates, and given that you have a set amount of charge on the plates, how to get the potential energy that's stored by those plates. All right, everybody. Our technical assistants are Sydney Geltrow and Sophia Turner. The funding comes from the University of Mississippi and University of Southern Mississippi. We film these videos in Hattiesburg, Mississippi. I'm your host, Dr. Christopher Sorolla, thanking everybody for your attention, and clear skies.